There are two types of intramolecular bonds. Bond between atoms that holds them together. We've already discussed the ionic compounds, so there's ionic bonds. And then now we've been talking about covalent molecules using covalent bonds. Ionic compounds transfer electrons, and then covalent molecules share the valence electrons. So let's take a look at how a covalent bond works. Within a covalent bond, there are two types. There are polar bond and there are nonpolar bond. The bonding is all about the valence electrons and how they share. So sharing is not always the same. So let me show you. If we start with a molecule like this, green usually indicates a halogen, which is a group 7 element, has 7 valence electrons. By themselves, they're not satisfied. Okay, one example is chlorine. Chlorine has 7 valence electrons, but it wants an 8th to have a complete outer shell so it can be stable. I have 2 chlorines bonded together. This would be what's called a nonpolar bond. The reason it's nonpolar is because the electrons are shared exactly equally. If we put this on the board and take a look, you can see 7 electrons here, valence, 7 valence electrons here. If they share right there, each atom, 2, 4, 6, 8, 2, 4, 6, 8, each atom has 8 valence electrons now, due to the sharing. And this sharing is equal. The electrons spend the same amount of time with both atoms here. It's called a nonpolar bond. If you did the electronegativity difference, chlorine minus chlorine would be 0. Another example would be hydrogen. Same thing, you have hydrogen sharing an electron with itself, so it completes its outer shell. But let's compare that to a bond that looks like this. This is different. This side's green, this side's white. So already you know there's a polarity involved. And polar simply means there's a difference in alignment or a difference in orientation, kind of like the north and south pole of the Earth. We have a polar bond. But let me show you what it looks like on paper. If we draw hydrochloric acid, we have hydrogen donating 1 electron to the bond, chlorine donating an electron. So both now are satisfied. But what I want you to realize is if you drew this, the electron would spend most of its time around the chlorine. Chlorine is a nonmetal. It has a higher electronegativity than hydrogen. So the electron spends most of its time here making that end relatively negative and this end relatively positive. It's called polar. So we have a nonpolar bond, electrons are shared equally, and we have a polar bond where the electrons are shared unequally. But there's a third kind of covalent bond which is polar, and it's a special case. It's called a coordinate covalent bond. And ammonia, the ammonia here, is an example of a molecule that has a coordinate covalent bond. If we look at the dot diagram of ammonia, its valence is complete around nitrogen, 2, 4, 6, 8, so it's satisfied. This is a stable compound. This is ammonia. But notice at the top, there are 2 unshared electrons, which actually makes an electron cloud that's relatively negative on this end. If we have over here hydrochloric acid, which would look like this, if you put hydrochloric acid in water, it dissociates, means it splits up. That H plus now is free. It already gave its electron here to chlorine, so it has a positive charge. So now if you brought that hydrogen over here, that positive to negative is an electrostatic bond. So it changes ammonia to become ammonium. So it actually would look like this. You have an H all the way around. But it does have a positive charge. Watch that here. We've got hydrochloric acid. If I put it in water, it breaks it up. So you have the chlorine with hydrogen's electron. This is now a positive ion. And then I have ammonia here, which has that unshared pair of electrons right here, which are relatively negative. And this positive hydrogen comes and it forms a bond, which will end up looking just like this. Ammonia, ammonium, 2 completely different compounds.